Alright, hell yeah. So on YouTube, this caver dropped a huge rock into a cave, and it fell for 9 seconds, and I was able to copy the video and kind of exactly get that. And it was almost exactly 9 seconds, so that's what we're going to use. And what is that 9 seconds? That's when he drops it, we're going to clock it, and then in the video you can hear a sound. So the rock hits the bottom, and then the sound has to travel back up to the caver's ear. And that's what we're getting. And for this video, we're going to try to find a solution from an iterative process. And I always like that because it's in the process of guessing. And I already made a quick video on how to get a guess. And so we'll go over that because we're going to use that for the iteration. And then hopefully we hone in on an exact answer. For this video, I'm going to use gravity as positive 10. And even though we're dropping it in the negative, direction, I'm just going to say that's the positive direction, And we're starting with a height of 0, and we're just trying to get the net distance that this rock travels. So gravity is 10 meters per second per second. Now if you read it like this, it's really good to see that we have a change in speed of 10 meters per second every change in 1 second. Kind of a better way to write it. And so we're saying, hey, something's happening in 9 seconds. And so let's start there. And I'm just going to, first assumption is to say that the rock hits the bottom of the cave at 9 seconds. We're neglecting, the sound travel. Okay, so how do we use this acceleration equation? Well, let's just do 1 second. After 1 second, acceleration says we're changing our speed by 10 meters per second every 1 second. Okay, so after 1 second, we're going 10 meters per second. At 0 seconds, we started at 0 meters per second. At 2 seconds, what are we happening? We went another second, we're going to increase our speed by another 10 meters per second. So now we're going 20 meters. And then so forth. So at 9 seconds, we have a velocity. Our velocity at 9 seconds is going to be 90 meters per second. And so, but now for these kinematics problems, and especially when just guessing, never forget this next part, is that, what we have is a rock being dropped. Its initial velocity is 0 meters per second. We're saying it hit something going 90 meters per second. So we need to find the average velocity, because we can't just use this 90. It's not going 90 meters per second the entire time. We can't use this 0, so you can also think of that. So it's the halfway point. It's this plus this divided by 2, or just, especially if we start with the 0 velocity, it makes these real easy. We have an average speed of 45 meters per second. And we're going that average speed for that time of 9 seconds. And then so sometimes I like to use the units are the equation. So I have seconds, and then I have meters per second. Okay, if I multiplied these, we would get meters. Seconds would cancel and we would get meters. Yeah, I'm glad I did that. Okay, so 45 meters per second for 9 seconds. And so that's going to be 45 times 9. And that's a total distance of 405 meters. Okay, hell yeah. And now in my physics book, it says the speed of sound is 336 meters per second. And if I think this depth is at a distance of 405, it takes sound travels at a speed of 336 meters per second. So it's going to take more than a second for that sound to reach that climber, that caver. Okay, so we need to account for that. Again, the units are the equation. We have meters. I'm just going to leave meters down here because, hell yeah, if I did this, meters would cancel, seconds would pop upstairs, and so that's what we're going to do. So 405 divided by 336, and we get, and I'm going to store this as, I don't know. I'm just going to store that time as 1.205, and so this is the time that the sound has to travel. So now we do our kind of like the first iteration process. We say that, this rock did not fall for 9 seconds. 1.2 seconds was used getting that sound to travel back to our ear. So I'm going to take 9 minus that 1.2. And then I'm going to use this as my new time value. So I'm going to say t is 7.79. In my calculator, I'm going to store it as a letter t. So I'm going to store this as t. And now we're going to go through that same process again. If this is my new t, every second I'm picking up that velocity. So, and don't get the decimals confused, because if I was going for time is equal to 7 seconds, I'd be going 70 meters per second. If I had a time of 7.7 seconds, I'd be going 77 meters per second. So right here, I'm going to multiply this by 10, and my velocity at this time is going to be 77, basically 77.9 meters per second. So I'm going to just multiply this by 10 and keep these in my calculator. Alright, so that's going to be again, that's just the max speed of the rock. We started at 0. I got to divide that by 2. This is now our new average speed. We thought it was 45. That was too high, because a lot of that time, 1 second of that time, was used for that sound to travel up to our ear. So this is our new average speed, 38. And the new time is going to be this. So we're going to take this new average speed of, so we take this, divide by 2. We get this new average speed of 38.9. And we're going to multiply it by that new time. So multiply it by that time, and we get a depth of 303.8 meters. Okay, hell yeah. So now if this is our depth, this is where we need to get another equation. And I wanted to make this video like using no calculus. Like what did we do here? We took our time, so we had some sort of time value. We multiplied by 10, we divided by 2, and then what did we do? We multiplied by the time value again. And that's how we got this distance. Cool. And then so I have this distance, and what I'm interested in is what's the time. So what I'm going to do is just solve for t. So here we have t squared, and then I'm going to get this 2 upstairs, the 10 downstairs. So I'm going to have 2 divided by 10d, which is just d divided by 5, and I'm going to get t by itself. So that's the square root of the distance divided by 5. Hell yeah. And then in my calculator, I'm going to say this distance is just the variable x. I'm going to store that as x, because I'm going to show you the iterative process that I go through. So then this time is going to be the square root of the x, which is that distance, divided by 5. Okay, let's do this. So we got square root of x divided by 5. And then we have a time of 7.7946. And what's our time? Well, that's going to be the same number. Hold on. Alright, hell yeah. Now this is the part of the video where, oh yeah, I just did this about half hour ago. I think that was unnecessary. Okay, so the iteration part of this is that if I'm thinking this is the actual depth of the cave, and yeah, so yeah, this is interesting. I even need to take a pause. Huh? Yeah, that's funny. So yeah, the iterative process comes from, we guessed 405. And then we tried to guess the time the sound traveled up to the caver's ear of 1.02. And then we used that to crop our time. Our time wasn't 9 seconds, it was subtract that. And then we get a new distance. Well, that's where we are in the iterative process. So sorry for going through that, but sometimes it's just like, well, I don't know how to do an iterative process. And honestly, I don't know a proof for an iteration. I just kind of know, like, sometimes it works. And so what we're going to do is we're going to take this value and divide by that speed of sound, 336 meters per second. Meters cancel, and we have sound. So we have this distance divided by 336, and this is our new time. So we have a time of 0.904. And so if this is our time, what we want to do is compare it. Like this has to equal 9. I mean, this plus alpha t in our calculator, because we have this 7.79. These two have to equal 9, and we're going to see if they do. So we just did this 1.904. We're going to add it to alpha t in our calculator, and we're not at 9. We're at 8.69. So we have, so now we have too little time. We're using too little time to explain the experiment. And so we need to take 9, the time that we actually calculated, and we need to subtract that. And then so here's our difference. Hell yeah. And our difference is positive, so we need to add that. So I'm going to add that to alpha t. And so now I'm going to say the rock falls for 8.09 seconds. It wasn't 7 point, so we have a new iteration on this time value. I'm going to, and I totally apologize for doing something different, because now we can just run the iteration. So we have a new time value. I'm going to multiply by 10. That's our max speed. I'm going to divide by 2. That's our average speed. And then multiply by this new time value. And I didn't store the new time value as t, so I'm going to store that as alpha t in my calculator. And then take this average speed, the new average, times alpha t. And then so here's my new distance. My new distance is 327.7. We're going to divide that by 336. So I can store this as x if I wanted to. Divide by 336. So, and that's going to be the time for that sound to travel up. The time for the rate of descent until it hit, we were assuming was alpha t. So I'm going to add that to alpha t. And it's overshot now. So now I'm going to go 9 minus this, because 9 is the time for the whole system to do its thing, for the rock to drop and for the sound to reach us. And as we go through this iteration process, maybe I can explain it a little bit better. Okay, so now I'm going to take that alpha t. This alpha t was the time just for it to drop and hit. That's what we were trying to assume. But we overshot it this time. So I'm going to add it to that difference and reduce it, and then store it as alpha t again. So now this reduced time is what I think the rock is hitting. And so I'm going to multiply that by 10. That's max speed, divide by 2, and then multiply it by alpha t. Okay, hell yeah. And then this is the distance, I think this is the distance of the cave pit. And alpha t was the time we were using. So if this is the distance divided by 336, this is the time it takes for that sound to travel to my ear. This time plus the time that it takes to hit the bottom should equal 9. And we're getting there. So I'm going to go 9 minus this, and so we undershot it. And then but we're iterating towards an answer. All right, hell yeah. So now I'm going to add this to the drop time. So alpha t, this is the time of free fall of drop. Cool. So now I'm going to run that whole, and I'm going to store this as my new time of drop. I'm going to multiply by 10. This is the max speed, divide by 2, average speed, times that time of drop. So this is my new distance, divide by 336. That's the time for the sound to reach. This time plus alpha t should equal 9. Hey, we're getting really close. When we get to 3 decimal places, we'll probably do one more iteration. But hell yeah, that was 9 seconds. So now we know that the drop time, but we still have just a little bit different. So let's run this iteration again. So we're going to take the actual time that we clocked for both processes to happen, for it to free fall and for the sound to hit, has to be 9 seconds. So we do have a little discrepancy. I'm going to take the time of free fall and then add it to that difference. And then store this as my new time of free fall. I'm going to multiply by 10, divide by 2, and then multiply by that time of free fall. Average velocity times that time is the total distance. I'm going to divide by 336. This is going to be the time for the sound to go back up. And this plus that time of free fall should equal 9. And hell yeah, we're within 3 decimal places. So now I'm going to say the distance this thing falls under a gravity of 10 is 323 meters per second. 323 meters. And then the time that it takes the sound to travel back up is 0.96 seconds. And the time of free fall is 8.04 seconds. So there we go. So those are kind of the numbers. Hell yeah. And for this one, I think we all kind of want to know exactly how deep this cave is. So let's use G as 9.81. Alright, hell yeah. So what we're going to do now is iterate using acceleration of gravity as 9.81. I'm going to store this in my calculator as X. Hell yeah. And we're even going to improve the iterative process. Because the first go round it didn't seem like I iterated. And it's every time you iterate it should be the same process. We're going to show that. And this is what I like to use. I like to use intuition to feel what the numbers are doing, and then go observe what the numbers are doing. And usually that's a pretty good dimensional analysis of if the numbers are doing that, dimensionally, things are going to be correct. And for this, gravity is constant, and so we just have a linear change in velocity. So all we're doing is finding the average velocity and then multiplying it by the time. But time comes up twice, because to find the max velocity, you have to take this time and multiply it, because this is in meters per second per second. That's what meters per second squared is. That's the units on acceleration. Alright, so let's walk through this. So if we have 9 times 9.81, I'll at least spell it out for the first couple. This is going to be my max velocity after 9 seconds. Cool. And so that's where the max velocity is. This velocity is 0. This is max. We need to know our average velocity, so we just divide by 2, because it's a linearly increasing in speed. It's not something quadratic. This is our average velocity for that same amount of time. And this is where I'm going to input 9 into my calculator as t, just because that's what we were using for our iterative process. So I'm going to take this average speed times t, and this is our distance, 397. I'm going to divide by 336 for the speed of sound, because if this is the depth that we think this cave is, now it's going to take 1.18 seconds, and so that's the time for the sound is going to be 1.81. So here's our iteration. We need to say that this was the time that time for the drop. So I'm going to say time for the drop plus time for the sound, and I'm going to calculate that. That's going to be 9 plus this, and that's going to be 10.18, which is too high. That's bigger than the actual value of 9 seconds, which we know is the true value. So I need to find the difference. I need to take the true value of 9 seconds and then subtract. I'm going to find the difference, and so and that's going to be this value. And again, we're assuming 9 seconds for the entire fall, and then we're adding back in the fact that it takes 1.18 seconds for that sound to get, and that's going to be overshot. But now we're going to say, well, it should be 9, and so let's find the difference between those. So I'm going to go 9 minus this is negative 1.18. So now what we can do is we can take our time drop and then subtract this difference, or add. We're going to add the difference. And this is going to be our new, so this is the iterative. This is our new time drop. So our new time drop is the old time drop, t, plus this change. And I'm going to store that. So now that's that 7.81, and now we're on our way for this iterative process. Hell yeah. So now this is now stored in my calculator as t. Now I'm going to go a little faster. That time times gravity, so I'm going to go tx. that's my new max speed, divide by 2, average speed, and then for that amount of time times t. Now all we did there was just 1/2 x t squared, 1/2 gravity t squared, but I like the way that we do the order. We're saying this is our free fall time, and that's the time that gravity is going to pick up that velocity. So this times that is our max velocity. We started with 0. We find the average by dividing by 2. And we take that average speed and multiply by that time again. I just think it's a better way to go. So let's do that whole process again. So we have alpha tx, max speed divided by 2 times alpha t. And so here's our new distance. I'm going to divide by 336. So this is our new time. And I'm going to add it to our drop time. So this is 0.89 is our time for the sound. I'm going to add it to the drop time. Those should equal 9, but they don't. So I'm going to take the difference and then add that to my drop time. So now my drop time just increased. And now what we have is 9. We're going from 9 to low. We're going too high, too low, too high, too low, and we're iterating. So now if this is the new drop time, I'm going to multiply by gravity, divide by 2 for the average speed, and multiply. And I forgot to save this as t, so I need to save that as my new t. I'm going to take this average speed times t, and then that's the new depth of the cave. We're going to divide by that 336 for the speed of sound. Now the speed of sound is 0.95. We're going to add that to our drop time. Hopefully it's 9. We're getting closer. So this iterative process is working. I'm going to take 9 minus that, and I'm going to add that to my drop time. So now this drop time was too high. So now we have 8.04. We're kind of going back and forth. Here's the new drop time times gravity. I'm gonna store that as the drop time. Multiply by gravity, we got the max speed. Divide by 2, our average speed. Multiplied by t, because that's how long we're traveling that average speed for. This is our new depth. Divide by 336. This is our speed of sound plus our drop time, or the time for sound plus the drop time should equal 9. We're still off. Find the difference, and then add it to t. So now we boosted it up. We're 9.05, almost 9.06. I'm going to store that as alpha t times x divided by 2 times t. Divided by 336 plus t, and then 9 minus that. And so with this iterative process, now you can just kind of crush it out. Plus t stored as t times x divided by 2 times t. And if you do so in a way where you're just like, okay, I'm trying to get the max speed, dividing it. Now I have distance. Now I'm trying to get the time for the sound. So divide by that. I'm going to add it to the drop time. Hopefully it's 9. We're going to divide it from 9. And yeah, we're pretty much there. We're going to do one more iteration. Hell yeah. And so I'm going to, this is the difference plus alpha t, and then store that as alpha t. So hell yeah. So we're 8.05. Is the drop time for this. So when we calculated at 9, there was a full second, and that makes sense. If the depth of the cave is about 336, it'll take 1 second for that sound to come back, and only 8 seconds of it will be dropped. So this is this should be written up in a physics book, because it kind of just works out real clean, kinda. You know what I mean? 1 second for the sound to travel, and then 8 seconds for it to drop. So I stored that as my new alpha t times x, max speed divided by 2 times alpha t. And then here you go. So we're going to say the cave depth is 318. You know what I mean? And good enough. 318 meters. So that is and this is legit now. Minus air resistance, we have factored out the air due to the speed of sound. Due to, our only data was the fact that we saw this rock being dropped. 9 seconds later, we heard a splash from the bottom, and we know that splash or that crash has to, take some time to get to the caver's ear. So hell yeah, and this was way better then our approximation, if we did not take sound, it was going to be like 400 meters on average. And if we and if I did that first iteration, I got 304 meters. So even just doing a quick, assumptive iteration, or just one iteration, I guess that's what it was. I did one iteration. I didn't realize that. And after one iteration, we this is 33% error. What is one iteration? Minus 304 divided by the actual answer times 100. So after one iteration, you get down to 4% error. Because I can do one iteration in my head if I use G as 10. And so that's kind of what we did in that first video. Is like, hell yeah, you can drop something off and even get the accurate answer based on the speed of sound, just by going through that iterative process. First, just say it hit with the time that you clocked, and then find that first distance, and then if it's and then just divide by 300-ish. If we're dealing in meters, so this ain't going to be useful if 318 meters don't mean nothing to you. Because in America, yeah, I don't really know, Would I just multiply by 3, about 1,000 feet? So yeah, that's a deep cave, actually. Yeah, because 318 means nothing to me. 1,000 feet, oh hell yeah. That's even 200 feet's hella tall. Pretty tall. 1,000 feet, yeah, that's a cave. Alright, sweet. So we did an iterative process. Always fascinating. I'm always looking for them too. It's just like, when do they pop up? I guess they pop up when it comes to quadratics, because the solution is a quadratic equation. So I'll have to keep that in mind. That if do all problems with quadratic solutions, can they be solved with an iterative process? Anyway, alright, thanks for joining me, and that's a video.